right, let's talk about Chapter 7 here in Astronomy. Welcome back, everyone. Okay, we're going to talk about Chapter 7 here, which has to do with other worlds and an introduction to the solar system. Okay. To give an overview of our planetary system, we're going to talk about the composition and structure of the planets. We're going to talk about how to date planetary surfaces. It's not what you think. And we'll talk about the origin of the solar system. So, surrounding our sun are 8 very different worlds, a lot of dwarf planets, hundreds of moons, a million minor planets, asteroids, comets, all kinds of stuff. And since the 1960s, we have visited every planet and many of the smaller objects using robots to learn a lot about them. So in this chapter, we're going to talk about what we've learned about these things and then discuss the concept of comparative planetology, which is when we compare planets to each other to learn about planets in general. Okay, so let's start by talking about our solar system. So learning objectives from this chapter is we want to describe how the objects in our solar system are identified, explored, and characterized. We want to describe the types of small bodies in our solar system, their locations, and how they formed. And we want to model the solar system with distances from everyday life to better comprehend how far apart these things are. Okay, so our solar system, we've got the sun, the planets moons, rings, asteroids, comets, a lot of dust. Decades of observations suggest that all of this material formed together with the sun about 4.5 billion years ago. Planetary astronomy is the only branch of astronomy where we can actually make direct measurements. We send robots to the planets in our solar system, take measurements. We've talked about how astronomy in general is an observational science because we can't go to other galaxies. But in this case, we have a chance to send robots and go check them out. So this is the mass of the solar system. You see that 99.8% of the mass is occupied in the sun. So the sun is the most massive thing by far. The next most massive thing is Jupiter, 0.1%. All of the other planets and dwarf planets combined are less than the mass of Jupiter. Okay, just to give you an idea. So the sun, a giant burning ball of hydrogen, contains 99.8% of the mass of the sun. Jupiter, 0.1%, everything else, 0.04%. Mercury, Venus, Mars, Jupiter, Saturn, they were all visible to the naked eye, so everybody has known about them forever, as long as humans have had eyes. Uranus and Neptune, though, were discovered after the invention of the telescope because they're too far away to see. The 8 planets all revolve around in the same direction as the sun. This is a key point that you're going to hear all the time. You've got the sun and you've got all the planets going around the sun in the same direction that the sun rotates, okay? That's a key hint. That's related to angular momentum. So they orbit in approximately the same plane too. So if you have the sun here and you have all the planets, they're orbiting around in roughly the same plane, like cars racing around a racetrack. There are also a bunch of smaller worlds out there, like Pluto, and Pluto is one of a class of objects called TNOs, or trans-Neptunian objects. They are way out beyond Neptune. And the largest of these objects are dwarf planets like Pluto, but there is a dwarf planet in the asteroid belt. And that's Ceres here. Okay. You can see the blue lines here are the 8 major planets. And you see how Pluto is one of the red lines, but it's not quite in the plane. It's askew, so it's not orbiting quite in the same way that the other objects are. And these are other dwarf planets here, Makemake and Eris and things like that. They're orbiting, they have more highly elliptical orbits. They are more inclined compared to the ecliptic, so they're just a little bit different that way. So the planets also rotate around their own axis, mostly in the same direction as they revolve around the sun. So what does that mean? It means here's the sun. It means the Earth is going around the sun like that, but then the Earth is rotating around in the same way that it's going around the sun. Now, of course, Earth is slightly tilted a little bit. Its axis is a little bit tilted, so that 23-degree tilt, that's why we have the seasons. So we say that it's mostly, if this is the sun and this is the Earth or the other planets, they mostly orbit perpendicular, which means a 90-degree angle. And again, in the case of the Earth, it's 23 degrees, so a little bit less than perpendicular, but still kind of, still kind of like that. This is a key detail to get because the other planets are a little bit weird. So Venus rotates backwards very slowly. So a day on Venus is like almost a year. Pluto and Uranus rotate around they're tilted, they're on their side basically. So if this is the sun and this is Uranus, then Uranus actually spins around that way. So if our axis is, so if this is Earth and our axis is like that, that's Venus, and its axis is like that. Okay, so it's basically pointed at the sun and rotating around. So that's very skewed. That means Uranus has some crazy intense seasons because half the time it's pointed directly at the sun, the other half of the time it's pointed away from the sun, so it has a really long winter. Okay, so the 4 rocky planets, Mercury, Venus, Earth, and Mars, are the 4 closest planets to the sun. They're called terrestrial planets, and we usually lump them in with the moon. Okay, so we consider the moon like Mercury or the other planets. Our moon has a capital M. Every other moon has a lowercase m. That's just something you'll notice. The terrestrial planets are relatively small worlds, composed mainly of rock and metal, so we don't have a lot of gases here. All of them have solid surfaces that bear a record of their geologic history in the form of craters, mountains, and volcanoes. So Earth has mountains that are constantly changing, volcanoes that are constantly erupting, oceans and streams and everything, erasing a lot of its geologic history. This is the surface of Mercury. You can see that there's craters upon craters upon craters. So some very old craters that you can barely see evidence of. Not a lot of geologic processes ongoing on Mercury to erase those things. So they don't have volcanoes to put lava and repave the highways over there. They don't have wind and rain to erase them. So these are well preserved through a very long time. The next 4 planets from Mars, you got Jupiter, Saturn, and so on, up through Neptune, Jupiter, Saturn, Uranus, and Neptune. They are sometimes called gas or ice giants, depending on which one you're talking about. They're made of ices, liquids, and gases that are ice, liquid, and gas on Earth, in the phase on Earth. We call them Jovian planets, or the giant planets. For example, more than 1,400 Earths could fit inside Jupiter. That's a lot. They do not have solid surfaces, actually. So if you were to skydive onto Jupiter, you would just keep skydiving. You would never finish skydiving until you died, which is kind of like skydiving on Earth if you didn't have a parachute. Okay, on Jupiter, even with a parachute, the radiation would kill you before you even did anything. Okay, it took a dark turn, didn't it? Jupiter is a beautiful, wonderful place. Never leave Earth, it will kill you. All right, this is Earth. The universe is terrifying. Jupiter, Saturn, it's kind of like poison ivy. It kind of looks nice, I don't know. I'm terrified of it though. Okay, these are the gas giants. Next. This is Pluto. Pluto is an icy ball way out on the edge of space. We finally got there, New Horizons. We've got a probe over there to take some pictures of it. And we saw that it was a pretty interesting place, actually. It has a large icy region and some mountains down here with craters on it and some other mountains. It's pretty cool. Okay, so these are the planets. These are how far away in AU they are from the sun. So that means Mercury is 40% the distance the Earth is from the sun. Venus is 75%. Earth is 100%, 1 AU. Mars is 1.5 times. Jupiter is 5 times the distance from the sun as Earth. Saturn is 10 times. Uranus is 20 times. And Neptune is 30 times. So these are just some ideas. And here's your Kepler's law. That tells you the revolutionary period is linked with the distance the planet is from the sun. So you see the further away the planet is, the longer its year is. Mercury, it takes 25%, a quarter of a year to orbit the sun. Earth takes 1 year. Mars takes almost 2 years. Jupiter takes 10 years, 11 years to orbit. Saturn takes 30 years. Uranus takes 84 years. Neptune takes 165 years to go around the sun. And these are the diameters. So you can see that Jupiter and Saturn are very large compared to the other planets, and the other planets are quite small. You see Mars is really small, about half the size of Earth. And then what's really interesting is the masses here. So pay attention to that, because even though Mars is quite a bit bigger than Mercury, the mass is only twice as big. Okay, so diameter and volume goes like r cubed, so you'd think that it would have a more mass differential than just 6 times. So, I mean, look at this. Mars is half the diameter of Earth, but look at that, it's almost 10 times less massive. So it's a light planet, let's put it that way. And so on. And then you got Jupiter, which is just like, ridiculous. Okay, so most of the planets have, let me just say one last thing about that. The density, so you can see Mars's density is quite low. So the density tries to cancel out the effect of the diameter and the mass to put them on the same level. And so you can see that Mercury, Venus, Earth have similar densities, but Mars is pretty low, and then the gas giants are very low because they don't have much rocks in them. So most of the planets have one or more moons, except for Mercury and Venus. They have no moons. More than 180 moons are out there. There's a bunch that we haven't discovered, we're pretty sure about. The largest moons are as big as small planets. For example, Earth's moon is quite large. Jupiter's 4 moons, which are called the Galilean moons because Galileo could see them with his telescope. And then Saturn's moon, Titan, and Neptune's moon, Triton. Easy to confuse those names with each other. Each of the giant planets have rings. You may have known that. Saturn obviously has rings, but so do all the other planets. Jupiter has a tiny ring system. Uranus and Neptune, they're big ring systems, but they're just faint. You can't see them as well. They are made of grains of really fine dust grains up to things, big chunks, floating around. There's also asteroids between the orbits of Mars and Jupiter. Beyond Neptune, you have your comets, which are basically just frozen, dirty snowballs. There's a mixture of ice and dust. This is an asteroid. And this is a comet, Churyumov-Gerasimenko, humanity's first flyby of a comet. You can see it actually looks like it's 2 objects that got stuck together and are now permanently fused. And you can see they're glowing off the gas and dust. The solar wind is evaporating it. And then finally, there are, what are we talking about in this whole chapter? We're just telling you about all the things that are out there. So you're just building a vocabulary, you're getting a concept of what's out there. So that's all this is, basically. And then finally, there's just loads of dust, pea-sized chunks or smaller, sometimes bigger, just floating in space. And the Earth is constantly sweeping it up. When a pea-sized piece of rock enters the atmosphere, it lights up like a meteor, and we call it a shooting star. So shooting stars, meteors, the bright whoosh, are usually very small rocks burning up. Sometimes they're bigger. If they survive that and make it all the way down to the Earth and you can pick it up, it's a meteorite. That's the name for it. And you can check those out. Okay, then there's a scale model of the solar system here, and for this, what I want you to do is go to this website. And you can do it now or later, but this is a really fun way to get an idea of the emptiness of space. It's basically if the moon was the size of 1 pixel on your screen, how far apart would all the things be? Okay, so it's pretty wild. Okay, 7.2, composition and structure of the planets. What we want to learn out of here is define the characteristics of the giant planets, the terrestrial planets, and the small bodies in the solar system. Explain what influences the temperature of a planet's surface, and then explain why there is geological activity on some planets and not others. So on the giant planets, Jupiter and Saturn have similar makeups as the Sun. This means, and this is an important thing, make sure you know this because when we talk about stars, it'll be useful to know. The Sun is made up of 75% hydrogen and 25% helium. That helium is coming from the hydrogen being burned into it. So a quarter of the hydrogen in the Sun has been turned into helium, basically. Almost. That's almost true. Okay, we'll talk about it later. But Jupiter and Saturn are similar in their compositions, about 75% hydrogen, 25% helium. On Earth, hydrogen and helium are gases, so we call them gas giants. But that's misleading because the pressure is so great that on Jupiter, most of the hydrogen and helium is liquefied at the core, So we could call them liquid giants instead of gas giants. The terrestrial planets, like Earth and Mars, are primarily made of silicates, which is a combination of silicon and oxygen, and the most common metal found in them is iron. And that's an important point too, so pay attention to iron. You're going to see that come up when we talk about stars. So we can tell from their densities that Mercury has the highest proportion of metals because it has a slightly higher density than the other planets. And we think that probably Mercury got hit with something and the outer layers got blown off somewhere and only the core remained. So Mercury is basically the core of a typical planet. Earth's moon has the lowest density, and again, something hit Earth to make the moon. So the moon is primarily made out of Earth's crust, and Earth's core is heavier, has more metals in it. So Earth, Venus, and Mars, they're roughly the same composition, about a third iron, about 2/3 silicates. The most dense regions are at the core of the planets, and the lighter elements are around the perimeter. This is because the planets are hot enough to liquefy the rocks, and this means the heaviest stuff will sink and the lightest stuff will float. This process is called differentiation. So it's just like if you let salad dressing sit for too long, the oils and vinegar separate from the garlic and everything, and you get the layers, and you got to shake it up before you pour it on your salad. Same thing happens when planets sit for too long. The iron sinks to its core and the lighter stuff floats around at the surface. And that process is called differentiation. That's why the Earth's crust is very light and fluffy, delicious, and Earth's core is very molten iron. Okay, so generally the farther you are from a planet or a moon from the sun, the farther a planet or a moon is from the sun, the cooler its surface, because the further away from the sun you are, the less light you get. For example, Mercury's surface can get as hot as 400 degrees Celsius when it's facing the sun. Pluto's surface, the highest temperature it reaches in the summer is minus 220 degrees Celsius. So that's important relationship. So when we talk about the habitable zone around a star where we're most likely to find life, that's going to be in a region where liquid water can exist, where the sun provides enough heat, or the star of that solar system provides enough heat. You're close enough to get enough heat to keep liquid water. That's the Goldilocks zone, or the habitable zone. Habitable. Habitable. Okay, so in addition to distance, the next most important contributor to the surface of a planet is the atmosphere. Without our atmosphere, Earth's oceans would be frozen solid. So our atmosphere, a very thin thing, it's like a piece of saran wrap on a basketball. The very, very thin layer of gas is what holds on to enough energy from the sun to keep our oceans warm. Venus's atmosphere is so thick, okay, it's hotter than Mercury, right? It's twice as far from the sun as Mercury, and it's twice the temperature. That doesn't make sense. It's because its atmosphere is 99% carbon dioxide. It's very, very thick, very, very hot. 900 Celsius all year round. That's like 2 times a pizza oven. Okay, you would die. We've sent robots to land on the surface and they immediately die. Okay, they've taken like a picture and die. Okay, so I think we're working on another probe, and I think it's gonna be inside a refrigerator. That's a joke. Okay, so geological activity. The crust of all the planets, blah, blah, blah. We're still on 7.2. Okay, so the crusts of all the terrestrial planets, as well as those of the larger moons, have been modified by internal and external forces. For example, asteroids will leave impacts and craters behind, but the interior, if it's hot enough, will drive changes on the surface, like volcanoes that will erase craters, or tectonic activity that will create mountains and push craters away. So some planets still retain heat from their formation, and you can think of them as like hot potatoes. Whenever you make a baked potato, it's always hot, no matter what. You have to cut it open and like let it cool off, otherwise it just stays hot. Other planets that are, if they're small enough, like the moon, like our moon, it's basically frozen solid. It's cooled off, it has no geological activity, so when you look at it, it's just gray and covered in craters. The larger the body, the longer it retains heat. That's just another fact. Okay, so when it comes to dating planetary surfaces, there's some learning objectives here. We want to understand how astronomers can tell whether a surface is old or young. And when we say old, we mean geologically old or young. How long has it been since it's had a makeover? And then we want to talk about the different methods for dating planets. Okay, there's an app for that now. So how do we estimate the ages of the surfaces we see on a planet or a moon? It's not necessarily the age of the planet itself, but it tells you how long the planet has been active or dead. Is it cold? Is it still hot? The simplest way to estimate the age of a surface is to just count how many craters there are on the surface. Every object in our solar system was exposed to roughly the same rate of asteroid impacts, and then geological process should erase them over time. So if you just count the craters on the surface, you know roughly how long it's been since they've had a makeover. Radioactive dating is another way to estimate the age of a substance. When an element is created, it doesn't last forever. It decays at a constant rate, leaving behind daughter particles. And this process is called radioactivity. So if you're the sun, for example, and you explode, or if you're a star, for example, and you explode and you create a lot of radioactive elements, and then planets form out of those, and then they're slowly decaying. If you scoop out some of that stuff and then count how many daughter particles there are compared to how many total particles there are, you can estimate how long it took. You can actually calculate directly how long it took to create that number of daughter particles. And that's it. That's all you have to do. So you find a chunk of iron, you scoop it out, and you measure how much of it is still the original stuff and how much of it is a daughter particle. And then and you know how long it takes for that to happen, what's the rate of decay, and then you can calculate how long. So for example, you started with pure, there's no name for it, it just says a radioactive sample. So it's a pure sample of something, and over time it starts to decay into this blue thing, and it turns into something completely different. But it happens at a very precise exponential decay rate. So if you measure this proportion of new stuff to old stuff, you know that it's been 2 half-lives, whatever the half-life is. Let's say it's a half-life of 1 billion years. Well, it's been 2 billion years, and so on. Okay, so here's some half-lives of things. The parent would be samarium-147. So if you find some samarium-147 and you measure how much neodymium is still in it, then you know by that proportion that it decays at a half-life of 106 billion years. So you can use that to estimate the age of something by how many other things. So we use uranium dating, iron dating. You've heard of carbon dating. For carbon dating is good for things that are several thousand years, so we use those for anthropological things. But that's the main thing. So we can take samples from the moon, for example, do radioactive dating on there to estimate the age of the moon. So everything we find so far, all the evidence points to a solar system that's about 4.5 billion years old. Okay, so let's talk about the origin of the solar system. The goal here is to describe the characteristics of planets that are used to create formation models of the solar system, and then describe how the characteristics of extrasolar systems help us model our own system. Then explain the importance of collisions in the formation of the solar system. So much of astronomy is motivated by trying to understand the origin of things. Where did the sun, earth, and the moon come from? One way to approach answering the question is to study patterns among the planets, including planets around other stars. So since all the planets orbit around the sun in the same plane, we can conclude that the sun and planets formed out of the same rotating cloud. This is an angular momentum argument. The angular momentum conservation argument. The planets are also made of the same substances found in the sun. So we see similar evidence in baby solar systems throughout the galaxy that planets and the stars form out of the same cloud. So this is a bunch of Hubble images of baby solar systems. These are star-forming regions where there's a baby solar system forming, and what we see is that a big cloud of gas or nebula is starting to collapse into a disk. And you can see these little disks here and those disks there, and these are called protoplanetary disks. And you can see the baby star systems forming with baby planet systems. So what do you get? You got a big ball of gas starting to collapse, and as it collapses, it starts to rotate and spin, and as it spins, it starts to spread out into a pizza, and then slowly over time, the little pieces start to stick together, just like cat hair in your hardwood floor into little tumbleweeds. The tiny bit of a planet or the tumbleweed component, the weed, is called a planetesimal. And then as they collide and together they stick, they start to form bigger and bigger planets, and that's how the planets came to be. And that's the whole thing. Okay, so we talked about our solar system, the things that are in it. We talked about the composition and structure of the terrestrial planets and the giant planets. We talked about how to estimate the ages of planetary surfaces using the crater method and radioactive dating, and then just the origin of the solar system starts as a cloud of gas, collapses, rotates, and the planets form from these little tiny bits. Okay, so that's the show. See you guys later. Bye.